Hi everybody. The name of this presentation is Ruby, Microservices, and Hardcore PostgreSQL. In the past, I did this presentation, this exact same presentation in Portuguese in a Ruby conference at Brazil, also virtually. And I decided after thinking a little bit that I want to translate some of my talks to English because some of the talks that I did are also interesting for people that work with the same problems and the same technologies that I am trying to solve on this presentation. So that's why I am doing a new version. I will try to keep it like the same questions and answers that I did in Portuguese and also the same format, but some differences may occur. If you speak both Portuguese and English, I'm going to link the original presentation here. So a little quick and dirty about me. My name is Mauricio Eduardo Chico Pochabo. I was a Ruby programmer at the time that I did this presentation, and in the past and also right now I am working right now with Clojure. It's an incredible language, it's a functional language, Lisp-based, and the idea of my project at the time of this talk was to try to use some of the Clojure concepts in the Ruby creation of a microservice. And that's the place that I live currently. It's a wonderful place called Uruguay, more specifically Montevideo. Okay, so what was the original project? It was an invoice emission, and it was a single system to emit invoices to multiple Brazilian states and also multiple countries. Each Brazilian state have a specific rule on how an invoice must be emitted. And when you extrapolate this to other countries, then the thing goes way out of control. Like there are multiple formats, multiple rules, multiple things. And at the first iteration, we decided to try a Rails project. But after thinking about a while, we had to ask our questions. Do we need some graphical interface? And to answer that question, the most important thing is, do we need manual intervention? What it means to have manual intervention in this situation is what kind of intervention that we want. Do we need to manually do things and tinker with our system to solve bugs? And what kind of bugs? What kind of manual intervention that we would do? And the other important question is, in which system do we need manual intervention? And what do we consider a bug in the invoice system and not in the other elements? It may not make sense, but it becomes really, really complicated when you put multiple systems in the stack, because if you receive an invalid message, is it a bug? If we receive an inconsistent message, is it a bug? And that's things that we had to answer. And also, there are automatic procedures that can help us. And to be honest, we don't need manual intervention on the invoice service. We decided to do an architecture where if we receive an invalid information, we just break. And if we receive an inconsistent information, we go on, but we can fix with future messages in other systems. So manual intervention will be not in the invoice system, but the systems that emit information for our system. So that was one of the design decisions that we done. And there are no automatic procedures that can help us. If it did, we wouldn't need to do this system anymore. And how was the company that I was working at the time? It was a big company. I am not going to share which company it was. It is on the original presentation if you want to know. But as it's a translation, I don't know if I do have authorization to speak more about it. And at the time, it was using a single company, a single system for all countries. And the system was monolithic. It started, I believe, as a CRUD system, create, remove, update, delete of clients, and evolved to a management system, and also was starting to do payments. And the payments is the full process, like scheduling the payment doing the payment that was extracted to an external system, so communicating with the companies that do the payment, for example, the credit card companies and other things. It was doing conciliation, also extracted to an external system because, well, it's really complicated. And we also had retries and chargeback also implemented in this monolithic system. And the last one it did was the invoice emission. That's what we're trying to extract. So the idea of the invoice emission was to try to fix some of the problems that we have. And the challenges are simple. Our data model is complex because, again, it is global. Multiple systems use, multiple countries use, multiple states use, and also deprecated. And that was complicated because at the past, we didn't need some of the payment information that we do need right now. And for people that are familiar with how Brazil works, some governments sometimes do not ask for, I don't know, a specific information, let's say a document number. And then, I don't know, in a year or two, they decided, no, we're gonna start needing this information. And this is complex because if we don't collect originally that information for the payment, we don't have it on our system. So we somehow have to work around this inconsistencies. And that's what I mean with historical data is incorrect. If a person didn't pay our system, well, no worries. At the past, people would not want to charge the person. But if that person wants to return to use our activities, it needs to pay all the historical debts that the person have. And that's the problem because our historical data is incorrect. It's missing information and other things, and we somehow have to correct that in the meantime. And what our original payment system, the invoice emission system, was trying to do is correct the historical data and emit the invoice at the same step. And this is quite hard. Our system needs to be ultra consistent because bugs are currently hard to find and we want to be better at that. And if we don't have ultra consistency, we are just spreading the bug. Like the original system do have bugs, our new system will have bug, and when something breaks, you don't know where it came from. So our new system will have to say, okay, you did give me this information, it's consistent starting from now. In the past, it doesn't matter. And also, we need to know if a problem exists from where it came. So we decided to do a state machine. And by state machine, I am not saying that we did act as a state machine. We did all of these things not by a specific state field in the database. We, for example, decided if a specific date, a specific timestamp is filled, then the invoice is in the state issued, for example. And we decided that the states are, I issue an invoice, and sometimes later, maybe individually, maybe in batch, maybe immediately, maybe at the end of the day. It doesn't matter when. It differs from country to country, to state. The invoice starts to get into the state processed. In this state, the invoice became immutable. Like you can't change a processed invoice. The processed can be success. It means I sent to an external system. Oh, to be honest, processed also can mean I sent to an external system, maybe an ERP system, maybe the government. And if I have a return from that system with a success, then that invoice is considered emitted, closed, and that's end. If it's not, then it's failure. And the failure state means that I can have a second version of that invoice with some new data that will follow the same life cycle. So a third and fourth and fifth version and so on and so forth. Also, it's messaging. So we can receive like inconsistent data. Like, for example, I receive a message here, then I get the message as issued, and then I receive a newer message. So it means that if the newer message differs and the invoice is not processed, we will update this invoice. Otherwise, if it's already processed, we break with an exception. So what Clojure have to do with anything? And to answer this question, I'm going to start by showing what we usually do in Rails. In Rails, we probably would have some kind of code like this. So I have an invoice. If the invoice is valid, I'm going to calculate tax, for example. I'm going to save it and redirect to action list. Here, if something breaks, I will throw an exception. So these are complicated because we are doing multi-step for a single thing, and they are all mutating the original invoice. So I decided on a specific data from an invoice. I am asking if it's valid, then I calculate tasks. So the valid or invalid is based on the data that I received, not if the tax can be calculated or not. And save will also change this invoice info. So it's hard to keep tracking on where the bug it is. Like, did I call valid? Yes, I did, but calculate tax failed. Why? Because probably it wasn't valid. So what I do, I change the valid, or I'll calculate previously, but it doesn't make sense to calculate tax if the invoice is not valid. So these are the questions that I want to answer with Clojure. And in Clojure, we do like to do this kind of impure code on the borders. That's what IO do. And pure functions as the core of our system. Pure functions are functions that only depend on their inputs and will not change the output in any way or change the word or other things. So for example, a sum is a pure function. We just depend on what we send as the arguments of the function. And random number generators are not pure functions because they have to somehow tell, okay, I did emit a specific random number, I want the next random number. So there's a seed and a position, and you keep generating the random numbers based on that seed and that position. So it's not pure code. Also, dates are not pure code. And that's quite complicated because it means that in our pure code, we can't have date.now, for example, or time.now. We have to somehow generate the now when we receive the message, and then start to work with that date, with that immutable date inside our functions. So the idea is we have a handler that's probably impure because it will read some information from the world, and then here we start to get the pure functions. Like we validate the format, and validating the format in this sense means just see if the format that we receive is valid. And that's kind of like an anti-corruption layer. So if I don't validate, I'm going to throw an exception, and we will know that the error is not inside our code, is from the system that sent a message for us. If I have to do something, I will have to do like APIs or databases and other things. I am going to do in handler. I can't do that in validate format. Otherwise, this validate format will also depend on IO code, and it means that it will become impure code. So the handler will probably send the message that we had already validated to a data merge, for example. So it gets information from the API and database. It merges this information in a way that makes sense. It will do some kind of text calculation and also return to a handler. And it will generate an output representation. You see that the handler is kind of like an orchestrator. It's not doing like code for itself, but it's calling on other elements that will enrich the original data and represent an output. What it means to represent an output is simple. I do not want to save a file, for example, in this situation. I want to return, let's say, a hash map, and that hash map represents, with little to no conversion, the file that I want to output. It means that it's easier to test than like save the file in the file system, and then read the file, see if the fields are there, and then close the file, so we don't have to work with temp files and other things. And in the end, with that output representation, I can insert into the database. Okay, but how? How Clojure does that? In Clojure, validate format is a hash map. So in this case, for example, I have a schema that maps one-to-one to the data that I am working. So I have a student that have a document that's the digits strings, so there's no like letters here. A full name is a non-empty string, and birth date is a date. And so on and so forth. System is finance or students, for example. So this is how validate format works, and you can see that the structure is easy to grasp. Like you see that there's a student and there's a sub-element document. If this is a JSON, you already know the format just by reading the format. And there's a library that will convert this data structure to a validator that will validate the data, and so on and so forth. And output representation is also the same. It's a hash map that inserts into a database. So for example, here I am asking to insert into the database people, 2 different fields. And also I can do a select from, so on and so forth. As you can see, the select from, it's easy to read, and also it's pure data. So you are not doing queries here. You are just representing the query with pure data on how you want to change. There's no mutation here. If I want to add a new from clause, well, I can't because it's joins, but if I want to add a new where clause, I will have to copy this information and then generate a new query. And that's actually good, because if I have 2 places that do queries and one do the query like this and the other in a different way, I can cache the query and everything will work fine, because the other place can change our queries. Okay, so let's start. Grabbing my gems, we decided to do messaging with Amazon SQS. Idempotency is a must, like we need to receive messages out of order or duplicated and so on and so forth. And the system must do what you expect, do the right thing. And it's kind of functional because it's not really that easy to do functional programming with Ruby. So yeah, here be monsters, because we are not using Rails, we are not using Active Record. And so most libraries are not that mature. Sorry. Okay, so the first monster was Rails. Like we tried to use Shoryuken gem and it didn't work well, because it expects either that you are using the action job over Rails or the Shoryuken script, and we didn't want to use that. So we decided to not use Shoryuken at all. We decided to do the concurrent Ruby with Amazon Web Services. So for example, we did use queues and a fetcher. I am doing extend self as a way to that poor man state class, if it makes sense. So fetch will get the queue, will map the queue, and so on and so forth. Here's some of the key points. Here's so that I can use fetcher.fetch. I don't need to create a class to do the fetch because there's no instance variable here at all. And also, I am working with pure data. I'm not wrapping it in an object in any way when I don't need. And as you can see, I just exit when the system quits. So there's no cleanup, there's no anything, because we don't want to have to worry about that. Sometimes the machine can simply die, and so we'll have to treat this anyway. So why bother? So the idea is that the process can stop at any moment, and you must be able to continue from where you started, from where you stopped. So that's that's a must. It's a requirement from our system, so that's why there's no like error handling at all. Also, the second, I didn't translate this slide, but I'm going to translate here. The domain-specific languages are also another problem. We have multiple formats per country, multiple formats per Brazilian state, multiple formats with optional fields. So, for example, in this case, integer is maybe, so it may be present or not, and there are multiple formats that need specific size requirements, like maximum size, minimum size. It can be a nil or it can't, and so on and so forth. We decide to use dry schema, but as you can see, dry schema is a DSL. So we have multiple formats per country and per state, and we have like a base format. So how do we merge DSLs? And the answer is you don't. Well, right now dry schema have a dot merge, but it's not clear how it would merge, for example, address with another schema that also have address. Will it aggregate everything, or will it replace one with the other? And what if I want to remove this field from a specific element, from a specific country, for example? Can I? Can't I? So that's one of the problems that we have to face. So we decided to change the DSL with a hash map. So this is real code. This is real Ruby code. It's exactly the same as Clojure format at least. And the idea is, from this hash map we generate the DSL. DSL is, well, the DSL. It works as you expect. So we can merge maps. We can join or remove fields or add fields at will, and the DSL will always be right because, well, considering that we did merges and it returned a valid schema, then the schema will be okay. Obviously, there's a lot of tests on this code. One of the important things to notice about schemas is not static typing. I am not typing an information. So if I do have a schema like digits string with a specific group of numbers, I am validating that it is a string, it only contains digits, and it only contains a specific number of digits, and that's all. For example, generator, I am telling here that there's only a single possible number of elements for that field. Or is this guy here is like general record or passport or I don't know, other things. In this case is identity card and so on and so forth. So these are the only elements that are valid for that field. It's not static typing when you have to just say, oh, this is just a string. Oh, there's dependent typing, but let's not go there. And also coercions. So for example, if I do have a schema like that, with generated at being a date and amount being a decimal, in this case big decimal, and text maybe is a string, I can generate from this hash schema. This is the dry schema, and I can coerce things. So for example, if I try to coerce my schema to an empty hash, it will say to me that generated that is missing and amount is missing. If I try to coerce generated that as a string and amount as a string and document as a valid document, as you can see here, the errors appear. In this case, the coercion happens, so date is now a date, even as I pass it as a string, and amount is a big decimal. That's how Ruby represents the big decimal to string originally. Oh, as you can see here, output amount class is big decimal. And as you also can see, document, it don't exist anymore because I am not expecting document on the schema, so it will remove that. And there's a reason for that. If you expect an element, it must be present. If you don't expect and you don't put on the schema, you start to get people like, oh, I'm going to induce the people that are working with this code in the future, I'm inducing them to error. So maybe because the moment is too fast, I have to deliver something really, really fast. I am not going to put this on the schema, and then after that I think how I would add it. And that amounts to eventually the schema does not represent the data that you want, so you probably throw away the schema, and also will throw away lots of validations that you can do that with that. So every field that's not on the schema is removed. So you have to add on the schema. It's not optional. And also the third monster is an objection relational mapper that's functional. Also again, typo here. So we wanted to be able to use different queries, and that means like customized PostgreSQL queries, and also to convert to immutable objects. This was quite hard. We want to disallow excessive updates, so it's not our objection relational mapper, let's call it like that. It can't allow you to just pick up a model and do update on it. Otherwise it will become active record, and I don't want like a poor man's active record. We did want something that you have to think about the queries before you write them. This would allow us to get consistency at query level, and also avoid N+1, lots of queries, no optimized queries. We decide to go to SQL with Anima. And that's when things, this is the way that we did. Like Anima is immutable struct for Ruby. So for example, in this case, we decide that the required attributes are these ones, and Anima new will always be the required attributes. So if we want to coerce a message, we just return, we just cache the JSON and the schema coercion, but it's immutable. I mean, there's no getter, there's no setter, you can't set anything here. Anima will also generate immutability at object level, so you have to clone the object, otherwise you can't change this object. And when we did a query with SQL, we just would create the Anima elements. Okay, I already talked about that. So what we did with Postgres was 2 tables will become 1 mapping. This is completely different from active record works. Like invoices will become like class invoices, and invoices version will become a class invoice version. And we decided to not do that. Like invoices plus invoices version, they will converge to a single object called invoice. And JSONB is used because, again, we have like multiple countries with multiple rules and so on and so forth. So we decided to do a JSONB. We indexed that JSONB so we can query for things. At the future, we could do custom index, like only index the invoices that are currently processing, not the ones that already are done. So we will have small indexes for everything. And we use it extensively the extended SQL from the Postgres. So insert into onConflict, it means that it's an upstart. Insert update returning is incredible because you are inserting and updating fields and doing a select at the same time in the same transaction without explicitly adding a transaction. And update from select, we'll see it a little bit later. So the life cycle of an invoice would be, if I was not using Postgres, I would have to select for update, but the invoice could be null. And if it's null, I can't continue. I have to insert the invoice, capture the exception because maybe another message came at the same time and now the invoice is already on the database. So I will try to insert. If it not exists, it will insert. If it exists, I ignore and do a second select for update. And this select for update will be inside the transaction. So we're gonna do the update if we can update, if the invoice is not in a state that it can't be updated anymore. And now I'm going to log process or crash depending on whatever path should I choose. We could remove everything with just a single query in Postgres. So I am inserting into the invoices. Let me see if no. So I'm inserting into the invoices and specific values. And if I do have a conflict on the indexes over these two elements, I am going to update set. So I do update only the external ID. In this case, I don't need to update the external ID because it will be the same that already is in the database. But it's just because if I do nothing, I will not get back the ID. So see how incredible this query is. I am trying to insert. If I can't, I'm going to just update an external ID from the value that's already there. And I'm going to return the primary key of this new or existing invoice in a single query. So I can replace everything for just the select for update. So I do this, and now I can do select for update over primary key, which is way better than doing by these two keys because now the query is faster. I am doing the update if I can do, and log process or crash. And if I can process, I'm going to update and end the transaction here. Why? Because I don't want to hold the transaction for too much time. So this will allow me to process messages in parallel, except when they are from the same invoice and same external system. So now if I do have like two of the same invoices being processed at the same time, one will have to wait. And as it's a transaction and I am not doing inserts here, I don't have the risk of deadlocks. The second situation that we had is sometimes we had sequential numbers for the invoices. Some countries need that, like you emit a single invoice, then you emit a second invoice, and then a third invoice. So you keep like emitting invoices, and you have to not repeat these numbers in any way, and you can jump between them. These countries probably, and most of the time, also want to emit the invoices in batches. So suppose I have 3 different invoices that are now processed, and the first and the third one failed. So now I will have to generate a second version of these invoices, but at the same time, maybe a new one came here. So now I have to update the version 2 with the name, with the original number and a new number for the version 1. So the process will be select of the invoices that are wrong, select of the new invoices that are not wrong, and I'm going to update the invoices new versions. So the new versions of the wronged ones will be updated, and I have to remove these new versions and calculate the digit for the new invoices. So all of this process can be done with Postgres. So how? I'm going to update the invoices version, and here are the interesting parts. Like the sequential number will be the sequential number of the original error the message. And if there's a range ID, I'm going to update that also. And errored is this second query. So I am doing a query where the sequential number is not null and the errors is not null. And see that errors is in plural because it's a array object. So I can have multiple errors in the same field without having to create a new table. That's one of the wonderful things. And the other is, obviously, I am getting the sequential number when it's not null and updating for all invoices that have errors. And I am returning when the second only for the invoices where the new version does not exist yet. and I am returning the ID that generated that and the new sequential numbers. So that's amazing. I'm literally getting all the invoices that failed and in a single step generating new numbers for it and putting it on the batch for new invoices. So what were the advantages that we had on this new approach? Well, the first one is because our process, our system, was occupying only 60 megabytes of RAM. And it means that we can scale it horizontally as much as we want. And the system boot was 2 seconds. The specs tests running were in 10 seconds. In fact, it was less than 4 seconds. So it's less than you boot Rails with Spring and with, fast startup gems for the whole system. So we always had the system booting, running the specs, and shutting down faster than we could in Rails, for example. Also runs in JRuby. We tried. Truthful Ruby, it did run, but not the SQS part, because at the time Truthful Ruby was not supporting SQS. And I tried recently to run in Truthful Ruby, but it's not stable yet. Like, there are things, for example, big decimals are behaving weird. But in the future, it will be perfectly fine to run into Truthful Ruby. So if we wanted, we could use the Java world and so on. And it's also Docker friendly. It means that it's a single process. So if that process stops working, we can recycle the machine and the process 100% and nothing will break. It's different, for example, when you have like Rails with lots of sidekick processes, because sometimes the Rails fail, the Rails server will fall, will stop working, but your jobs are still working, so you can't kill the machine. And in this case, it's just a single process. It can be rebooted anyway, and it will re-listen to every queue that we have in SQS. The test that we did, we tried to battle test it, and so we hired a DigitalOcean Kubernetes. It's a $10 node, 1 GB of RAM, 1 CPU. It's way underpowered for this kind of process. We put the PostgreSQL on the same node because we want to watch the world burn, obviously, and we try to emit 1 million invoices with random data. And obviously PostgreSQL couldn't handle that. So it restarted lots of time in the process, but the 1 million invoices were generated. Some had to take like 4 retries to be generated, but they did. So it means that our system was working correctly. And we did repeat the process with invoices, like with duplicated data and the same data for both invoices and so on. And we get similar results. So yeah, it was battle tested and it worked. And that's the end. At the original presentation, I asked if people had questions and if they had any comments and so on. So I ended with telling that maybe it's time to rethink about Rails, rethink if you need Rails for multiple processes or multiple code, and also be aware that if you are not using Rails, you will probably have lots of difficulties on some APIs, some systems that either expect Rails to be present or they are not updated at all. So be aware of that, but it's worth it, because sometimes Rails do some coercions and some strange things for you that you don't want if you need highly consistent systems. So the questions that I had was, at the original presentation, if I try to use Rails with some database like MongoDB Atlas, and I am not familiar with MongoDB Atlas. At the time I wasn't, currently I also am not. I did try MongoDB in the past. I got multiple consistency problems that I believe they are fixed right now, because I saw some posts saying that if you put some flags in MongoDB server, it will probably work fine. But I don't like MongoDB that much, because First, I think it feels that MongoDB is the jack of all trades and master of none. So while you can do multiple things with MongoDB, like use schemaless and use JSON and so on, Postgres, it's better than using like JSON, not the BSON of MongoDB. BSON contains like date time and so on. Postgres does not have date time as a data field. But I think that the JSON being Postgres was good enough. And to be honest, MapReduce, for example, in MongoDB, it's not that great. So there are better databases for that. So yeah, I don't really like MongoDB. I don't see MongoDB being used in a way that makes sense if you think a little bit more on how to model your data and so on. People also asked me if there was some moment when you thought, whoa, now this will not work at all. And yes, obviously, multiple times. We did try to use like immutable data for the RDM. We tried to use wrong RB, and we weren't able to make it work. It was quite magical and so on. So we decided to try to use SQL. SQL did have at the time an internal API that is class methods or something that allow you to do queries and decide how you will return them. So I tried to use that, but I saw that it was not documented. It behaved strangely in some edge cases. And I thought, oh, when I'm going to update SQL, I will probably break everything. So I just didn't use SQL at all. And what I used SQL, to be honest, was just because making queries with the Postgres database, with the Postgres adapter, it's kind of a pain. It's really hard. It's incredibly low level. We don't convert some of the data structures for you. Sometimes it returns strings for integers, at the time at least. So yeah, SQL was mostly like a SQL generator, and that's all. And also the Shoryuken, I tried to use the API that they said that it was an internal API that I shouldn't be using. I could keep using it, but I got scared, so I had to hack exactly what Shoryuken do without using Shoryuken at all. So yeah, some like problems in the meantime. The schema generator that we did, when I started the translation of HashMap to schema, I got into some bizarre edge cases of dry schema. Sometimes you had to use, they do have like similar DSLs for something. Let's say they have like field and string with field as the parameter. And while it supposedly had to behave in the same way, it didn't sometimes. So we got into situations where the external data were not being cut from the, for example, that moment that I told that we would remove additional columns. Sometimes it didn't work, like it just crashed the whole schema. Sometimes the coercion didn't work because we were using an API that was inverted, supposed to have to do the same thing, but it was not doing. And there were some breakages of APIs when we tried to update schema, and I was thinking, oh my gosh, maybe this will not work. So when I saw that it did work with like multiple edge cases, some cases that we probably would not even need, I felt more relief, and I decided, okay, let's go on with this. The serialization to big decimal to JSON, Rails do some monkey patches so that you can serialize big decimal to JSON. If you don't require JSON, you have to do the monkey patch yourself, and that was kind of a pain because we discovered that in production, when in Invoice was emitting with cents instead of like $10 or something. So What we decided was to do an anti-corruption layer. So we did make a bunch of tests that were testing how SQL works, how big decimal serialization works, and so on and so forth, to see if we will have some API breakage between versions when we updated. I know that's not a good practice to test libraries from the other people, but as I told in the beginning of this presentation, here be monsters. You're not using Rails, so it's not as battle tested as everyone else. So we tried to do that. Some of the tests that we knew would break, we got into pending. Pending of our spec is incredible because if you have a test that's marked as pending, it will not break when it fails, but it will break when it passes. So you know that the spec is fixed. So that's one of the things. And that gave us more confidence. But to be honest, what gave us more confidence was we passed through, I believe, 3 upgrades of Rails version, of Ruby version, the libraries version, the Ruby version, and nothing broke. So there we got, okay, we are doing the right thing. And the last question that I had was the creation or maintenance of the architecture was too complicated from our team? And the answer was, it was not complicated because the system is really simple. What was really complicated was for the people to exit the active record model. What means is that in active record, you can generate queries. The library will generate queries for you. So you just have to put some includes or some extends or some like preloads, and everything will be generated to you. But this also means that sometimes it's hard to know when a query will be issued. And that was not a thing that we could do in our invoice system. Because we emit like millions of invoices per minute, not per day sometimes. So there's specific dates in the month that we will have to pay the taxes, the annuality and the mensuality will be paid for the clients. So it means that in a specific day, especially after the paycheck of everyone, so in Brazil there's a rule that you have to pay workers at the fifth labor day on the month. So probably after the 5th day will be a lot more invoices than other days. And we can't like delay the emission of an invoice for 3 days, 4 days, and so on. So if we have, 20 million invoices being generated in a single day for a single country, for a single state, for example, you can't issue 20 million queries or more. Or let's say you have to at least emit 20 million queries, not more. You can't, for example, do an n+1 even by accident, because this will translate to, 1 billion queries in a small moment. So the idea was you don't have a query generator for you. You have to do the query manually. And that was complicated for people to understand at the beginning, because they were doing like, oh, maybe I can query and do first, and that was also not allowed, because first means I can return multiple elements. I want only the first, and no way. It's like, do the query and update at the same time. Do not keep information on the database for you. So that's why like update from select exists. That's why insert from update, returning exists. For update, no, insert on conflict, returning exists. So most of the time you didn't do the query manually. You did, or at least the active record model, like get the info, bring it to an object, I change the object and go back to the database. Most of the time it was a single query that will do everything. And that was quite complicated, because there were pull requests asking for helpers on making the query, and we would not allow that. And well, that's how things were. But well, that was most the problem. The infrastructure was really simple. We were already using Kubernetes, so we just provided the Docker file and everything was fine. Okay, that was it. I hope you enjoyed, and see you next time.